The periodic table of elements is one of the most recognized images in the field of chemistry. You probably saw the periodic table on a poster in many of your school classrooms growing up, and the amount of periodic table-inspired apparel is probably in thousands. Although the periodic table of elements appears to be, at first glance, just an orderly way of organizing all of the known elements, it actually took years for chemists to decide on the exact arrangement of the table. In 1864, British chemist John Newlands was the first person to find a convenient way of arranging all of the 49 known elements. The point of creating a periodic table was to effectively summarize an entire science in a single page in order to make it easier for chemists to remember and predict the elements and their various physical and chemical properties. Newlands recognized that he could split this mission into two tasks. One, he needed to find a pattern between the elements, preferably one that linked together similar physical and chemical properties. And two, he needed to figure out a way to conveniently organize the elements so that the pattern clearly shone through on paper. In the end, his early periodic table had 7 columns with 7 rows each. Newlands arranged the elements in order of increasing atomic mass. His idea of arranging the elements by atomic mass was pretty insightful. When the elements were placed in this order, there was a clear pattern among the first 3 rows of elements. Newlands discovered what he coined as the Law of Octaves. Every 8th element in these first 3 rows had strikingly similar physical and chemical properties, like color, texture, and stated matter. Unfortunately, this template had a fatal flaw. Newlands' decision to order the elements strictly by atomic mass, in even rows and columns, led to the grouping of some elements with completely different properties. In his table, iron, a metal, was placed next to oxygen and sulfur, 2 nonmetals. This was too much for other scientists to handle, and Newlands' template was ultimately unaccepted by the scientific community. Back to the drawing board. In 1869, Russian chemist Dmitry Ivanovich Mendeleev proposed a periodic table design that also arranged the elements with respect to their atomic mass, with a few winning tweaks. Mendeleev was less strict about grouping the elements evenly. If a certain element didn't seem to fit in with the elements around it, he swapped the order around until the groupings made more sense. This distinguished Mendeleev's table from all the others. In the final draft of his table, the elements with similar physical and chemical properties were all grouped together. Mendeleev's rearranging led to the existence of gaps in his table, which he rationalized as spaces for the elements that hadn't yet been discovered. Using his periodic table design, Mendeleev proposed that he could predict the properties and atomic mass of the elements that would soon fill in the gaps. His predictions were based on his observation that by arranging the elements in vertical columns from lowest to highest atomic mass, the elements in the same row of his table had similar properties. When new elements were later discovered and observed to have similar properties to the ones predicted, it solidified Mendeleev's table as the favorite. Of course, Mendeleev's table wasn't perfect, and we can see that our modern periodic table looks virtually nothing like Mendeleev's early drafts. Although the periodic table has come a long way since 1869, we can still appreciate how Mendeleev's early insights on elemental organization changed chemistry forever. His actions kickstarted a movement that, with the help of other visionary chemists, eventually led to the creation of the modern periodic table. Now, however, with our greatly improved knowledge of chemistry and the quantum realm, we can appreciate the beauty of the periodic table in full. Although Mendeleev recognized that the elements grouped together in either the same horizontal column or vertical row of his table had similar properties, like reactivity, metallic character, and color, we are now able to look at the table more in depth and spot new trends that chemists in the 1860s couldn't even imagine. Back in 1869, the concept of atoms as the building blocks of life was a theory that was still being met with skepticism. Our current acceptance and understanding of the atom lets us look at the table today and have a deeper understanding of why the elements seem to fit where they do, and why they seem to have similar properties going down a row or across a column. In the modern periodic table, the rows are referred to as periods and the columns as groups. Each of the main groups has its own name to describe the elements listed. There are the alkali metals, the alkaline earth metals, the transition metals, the halogens, and the noble gases. The group, or family, that an element belongs to tells you a lot of information about that element. Elemental characteristics have a tendency to follow left to right or top to bottom patterns. Going down each of the name groups, it becomes apparent that each family has their own set of characteristics. For instance, noble gases are the least reactive family, whereas alkali metals are very reactive. If we were to pick one element from each family, for example, sodium and helium, we can assume that since sodium belongs to the alkali metal family, it would be more reactive than helium. We can spot even more trends when looking at the periods in the periodic table. Moving left to right across a period, the atoms decrease in size. Electronegativity, which is the atom's tendency to attract electrons, increases from left to right, and metallic character, which is the level of reactivity of a metal, decreases. Looking at the periodic table more broadly, the table also separates elements based on their character. Metals are on the left and middle of the table, nonmetals are localized on the right, and metalloids are sandwiched in between. In short, the thoughtful, meticulous way that the periodic table is composed makes it possible for chemists to easily spot trends and patterns between the elements without having to memorize all the different characteristics for each individual element. It's a scientific lifesaver.